So we have done the first part, the second part. Now let us do the third part. That is the curl of the vector field A. Curl of the vector field A. So the third part is curl of A. Okay. And we know that curl, this A is a vector field. So curl of the vector field A is given by 1 by H1, H2, H3. Then the determinant of this matrix H1, E1, H2, E2, H3, E3. In the second line, we have del by del U1, dou by dou U1, dou by dou U2, dou by dou U3. Then we have H1, A1, H2, A2, H3, A3. The determinant of this matrix. Okay. And we have known that H1 for cylindrical coordinates, H1 is 1, H2 is rho, H3 is 1. So this is nothing but 1 by rho. Then we have the determinant of this matrix. H1 is 1, E1 is E rho. So this is E rho. E rho. This is rho times E phi. So this is rho times E phi. This is H3 is 1. So this is only Ez. Ez. This is U1. So this is del dou by dou U1. This is dou by dou rho. Dou by dou phi. Dou by dou Z. H1 is 1. So this is simply A rho. A rho. This is rho times A phi. Rho times A phi. This is not A3. This is H3. H3, A3. H3 is 1. So this is simply AZ. Okay. Is this fine? This is H3. This is not A3. This is H3. Okay, let me expand this then. So this is equal to 1 by rho. First, let us take this. Dou AZ by dou phi. Dou AZ by dou phi. Minus dou by dou Z. Dou by dou Z of rho A phi. Okay. So this is times E rho. E rho. Okay. Plus rho times, from this we take rho, dou A rho, this one, dou A rho by dou Z, minus rho times dou AZ by dou rho, E phi, plus this one. This is dou by dou rho of rho A phi. Rho A phi. Minus dou by dou phi of dou by dou phi of A rho. A rho. This is Ez. So this is the expression for curl. This is the expression for curl of the vector field A in terms of orthogonal cylindrical coordinates. Okay. Now let us solve the fourth one. And what is the fourth one? The fourth one is the Laplacian operator of the phi, the scalar field phi. Okay. The scalar field phi. So let me write it on a new sheet of paper. So let me write it on a new sheet of paper. This is okay. D, the Laplacian operator of phi. Okay. So the Laplacian operator of the scalar field phi, this is 1 by h1, h2, h3. This is the formula. Dou by dou u1, h2, h3 by h1, dou phi by dou u1 plus dou by dou u2, h3, h1 by h2, dou phi by dou u2 plus dou by dou u3, h1, h2 divided by h3, dou phi by dou u3. Now let us substitute the values of h1, h2, h3, u1, u2, u3. So for cylindrical coordinates, h1 is 1, h2 is rho, h3 is 1. So this is 1 by rho. What is u1? u1 is rho. So this is dou by dou rho. Then within bracket, h2, h3 by h1, this is rho. So this is rho, dou phi by dou rho. Okay, rho dou phi by dou rho. Okay, plus next we have this. This is dou by dou phi. Okay, and h3, h1, 1, 1. So 1 by rho. 1 by rho times dou phi by dou small phi. Plus this is dou by dou z. Dou by dou z. Okay, dou by dou z. h1 is 1, h2 is rho. So this is rho times dou phi by dou z. Okay, this is fine. Then I multiply throughout by rho. Okay, 1 by rho is now I multiply it only. And what do I get? I finally get 1 by rho, dou by dou rho times dou phi by dou rho plus this rho is independent of phi. Oh, so rho does not depend upon phi. So I can take 1 by rho outside, and with this 1 by rho, it becomes 1 by rho square. 1 by rho square, second order partial derivative of the scalar field phi with respect to the angle phi. Plus this rho is also independent of z, so rho can be taken outside. So this rho and this 1 by rho, they will cancel out. We get only the second order derivative of the scalar field phi with respect to z. So this is the expression for Laplacian of phi. This is the expression for Laplacian of phi in cylindrical coordinates. Okay, this is fine. Okay. Next, let us calculate the Laplacian operator in spherical coordinates. Example, Example, express Laplacian of some scalar field psi. Let us call it psi now in spherical coordinates. So the solution here for spherical coordinates, here u1, the first coordinate is r, u2, the second coordinate is theta, and u3, the third coordinate is phi. In spherical coordinate, the first coordinate is r, the second coordinate is theta, the third coordinate is phi. Then the unit vector E1, the unit vector along the first coordinate is ER. The unit vector along the, sorry, this is not U2, E2. The unit vector along the second coordinate is E theta. And the unit vector along the third coordinate is E phi. Okay. This is fine. Then the scale factors. H1, this is equal to HR, and this is equal to, in spherical coordinate, H1 is 1. H2 is H theta, and this is equal to R. And H3 is equal to H phi, and this is equal to R sine theta. This is equal to R sine theta. So Laplacian of psi. Laplacian of psi, we have the formula 1 by H1, H2, H3, dou by dou U1, H2, H3 by H1, dou psi by dou U1, plus dou by dou U2, H3, H1 divided by H2, dou psi by dou U2, plus dou by dou U3, H1, H2 by H3, dou psi by dou U3. This is the expression for Laplacian of psi. Now let us substitute the values of H1, H2, H3. So this is H1 is 1, H2 is R, H3 is R sine theta. So this is 1 by R square sine theta. So this is 1 by R square sine theta, dou by dou U1. This is dou by dou R. Now H2, H3. This is R sine, H2 is R, H3 is R sine theta. Okay, so this is R square sine theta times, this is R square sine theta times del psi by del R, plus this is del by del theta. H3 is R sine theta, H1 is 1, so this is sine theta. Dou psi by dou theta. Plus dou by dou z, sorry, dou by dou phi. H1 is 1, this is R, this is R sine theta, so this is 1 by sine theta, dou psi by dou phi. Okay. This is fine. Okay. Then this is equal to 1 by R square sine theta, 1 by R square sine theta. This sine theta is independent of R, so I can take sine theta outside. Sine theta, dou by dou R, R square, dou psi by dou R. Plus dou by dou theta, sine theta dou psi by dou theta. Plus this sine theta is independent of phi, so I can take it outside. So this is 1 by sine theta dou 2 psi by dou phi square. Okay, now I divide throughout by r square sine theta. So this becomes 1 by r square dou by dou r square dou psi by dou r plus 1 by r square sine theta dou by dou theta sine theta dou psi by dou theta plus 1 by r square sine square theta dou 2 psi by dou phi square. Okay, so this is the expression for Laplacian of the scalar field psi in spherical coordinates. And this expression will be used frequently in your later classes. Okay, so that is all for today. Let me stop the recording.